All right, let's try to answer a few simple questions here based on the demonstrations we saw here and our description about magnetic fields generated around moving charged particle. So steel, right, is one of the types of materials that is attracted to a magnetic field. Okay, the one that experiences a force when it's placed in a magnetic field. That's what that screw was made of that I used in the demonstration. So if I have a bar magnet here where I have a north side and a south side, and I bring it next to the steel object and I know that the steel object is attracted to that magnet, what happens if I flip the bar magnet over? What's going to happen to the ball? Let me turn on the polling. What do you guys think? What happens if I bring the south end of that magnet close to the steel object? I'm going to go ahead and end the poll. Okay, so most of you said A, which is the correct answer. It's going to be attracted. So that neutral steel object is attracted to either side of the magnet, just like we saw that steel screw was attracted to either side of my magnetic dipole that I had when I had the magnets on my desk. What about this? If I take a compass needle and it can rotate on that pivot point, and it's in a positively charged rod. So now I bring a charged object, positively charged object near that compass needle. What's going to happen to that compass needle? Any ideas? Let's poll for this. What happens if I bring a charged object near the compass needle? Okay. Most popular answer right now is B, that it rotates counterclockwise. Well, let's think about this. This is a charged object that's just stationary. I just bring a rod there and it's sitting there. Is it going to generate a magnetic field? Well, if there's charge and it's stationary, right? If we go back to our rule here, to generate a magnetic field from a charged object, it's got to be moving. If I just have a stationary charged object, it generates no magnetic field. If there's no magnetic field generated by that charged object, it's not going to try to rotate the compass. Remember, the compass was rotating in the charge field. Well, what's going to happen? This is a neutral object, but that neutral object just experiences an attractive force towards the charged object. And the top side of this will have an equal force as the bottom side. All the sides of this thing will be attracted to this charged object. This is right. Remember, the sides of the compass needle doesn't have positive and negative charge. It's just this intrinsic dipole, right? They're separate. It's not charged, it's a neutral object, but it has this magnetic property. So the compass needle does not rotate if I bring it near a charged object. It only rotates if it's placed in a magnetic field. What about this one? What if I take a magnet and I chop it in half? Okay. What are the different ends of the magnet going to look like? Or what are the two pieces that I end up with? How are their magnetic properties going to look? All right, good. I'm going to stop it there. Most of you selected C, that we would end up with 2 separate dipoles. And at the point where they break apart, I have a north side and a south side. That's right. We saw that with that stack of magnets I had when I split that stack of magnets in half. At the point, right, you can imagine when I split that stack of magnets in half, that point where I break it apart, there's an attractive force that I have to overcome to get them apart. So I know that there's opposite sides there at the center, and as I separate them, I end up with 2 separate dipoles or 2 separate permanent magnets that are oriented in this direction. Okay, what about this one? I have a current, a wire that's carrying some current either into or out of the page here. And I place some compass needles around it. And I see that they orient themselves like this so that the north side of the magnets is going around like you see here. Can we figure out what direction the current has to point? What do you guys think? What direction does the current point? Okay, I'm going to go ahead and end the poll. So most of you selected out of the screen. Let's check that. How are we going to do that? We can use our right-hand rule. Let's just pick one of the compass needles. So the right-hand rule, we know our thumb is going to point in the direction of the magnetic field. Our index finger needs to align with the direction of the moving charges, right? That's the direction that the current flows. Remember, the current points in the direction of the moving charges. And then our middle finger points in the direction that we travel from that current out to that object. So, right, I can test that here. I need my thumb to end up, let's look at that top one. I need my thumb to end up pointing to the left. And I know my finger, right, my index finger has to point in the direction of the current. So if the current was flowing into the board, my index finger would have to point into the page. My middle finger would point up to that compass on the top, and that means the magnetic field would have to be pointing to the right. So that can't be right. If I flip it around and have the current pointing out of the board, right, out of the page, and then point my middle finger to that compass, well, now my thumb points in the correct direction, right, in the orientation of that compass. You can also do the idea where you point your thumb in the direction of the current and your fingers should follow the sort of rotation or sort of the flow of the magnetic field around the current. So here I can see that the current, or that the magnetic field is sort of circulating counterclockwise. So the current has to be coming out of the screen at us. And you can check at any point, right? Use the right-hand rule to show that the magnetic field is aligned here. So here I point my index finger in the direction of the current out of the page, my middle finger towards the compass, and then my thumb points in the proper direction there. I get a magnetic field that points down. What about this one? I have a positive charge. This particle is moving into the screen. Okay, so it's moving away from you as you're looking at it. What direction is the magnetic field point at this point here? By the way, Emma had a correction on the chat. She says that in that formula, it is newtons over amps meters. I believe her. That's probably correct. I don't remember off the top of my head the order of that. That collection of units, the reason I don't remember that collection of units, we just call it Tesla, and so you end up not remembering the sequence of fundamental units very frequently. Thank you for clarifying. All right, let's go ahead and end the poll. So the most popular answer was up. So let's see, our vectors are the velocity vector points into the screen. The R vector points out towards my object here. I can use my right-hand rule. I'm going to point my index finger in towards, right, or at, I don't know how you guys are looking at it. Maybe you're looking at a screen, in towards the screen, point my middle finger in the direction of R, and then I get that the magnetic field at that point has got to be pointing up. Look, the magnetic field always has to be perpendicular to the plane that's defined by R and the velocity, right? So you can imagine if I have an R vector and a velocity vector, those live in a plane. The magnetic field is always perpendicular to that. So here this makes sense. The plane is kind of this slice that's perpendicular to your screen. And so the B field either has to be up or down in this case. And we can see using the right-hand rule that the B field has to point up. And so we could use this to draw the magnetic field for a set of charges that are moving, okay? Let's try to fill this in. Let's draw the magnetic field at each of these points. So here I have a positively charged particle that's moving in this direction. So let's set up a sequence here. Let's say A is up, B is down, C is left, D is right, and E is, I don't know, into the page for this example. Let's make this one out of the page, into or out of the page. So let's look at this point here. What direction does the magnetic field have to point at that position here? Can we draw that? Let's see. Does the magnetic field point up, down, left, out of the page, into the page? Let's label our vectors while we're working on this. That's the velocity vector. They give that to us. What direction does R point? R points in this direction. So we can see that R and V vector are living in the plane of your screen. So the B field has to be perpendicular to that because it comes from a cross product. So that means it either has to point out of the page or into the page. So we can zero it down to D or E here. Let's end this, share the results. Okay, most of you selected D, that it's out of the page. Let's check. As I'm looking at the screen here, V is up, put my middle finger in the direction of R, and my thumb is pointing right at my face here. So the B field at this point has to be coming out of the screen. Okay. Any of the particles, the points on this side, right, are going to have the B field coming out of the screen. You can try the right-hand rule with all of those and get the B field is coming out of the screen. What about at this point? Maybe just type it into the chat. What direction does the B field point for this guy? What do we think? What direction does the B field point? Well, what direction is the r vector? My velocity vector is in the same direction. Now r points in the same direction as v. How do I do the right-hand rule? I point my index finger in the direction of v, my middle finger in the direction of r. Okay, well, I can't really do that and have a separation between my two fingers. Okay, so there always has to be some opening angle between r and v to generate a magnetic field. So that tells me the magnetic field here is just 0. I can't really use my right-hand rule when r and v are aligned. If I go back to my equations, remember there was that sine theta term when determining the magnitude of the B field. When the angle between r and v, right, that was the angle between r and v. When that goes to 0, the B field just turns off. What direction does the magnetic field point here? Well, now my r vector is in this direction. Oops. If I put v cross r, use my right-hand rule, I end up with magnetic field into the board. What about this guy? Here's a negatively charged particle now moving out of the page. So it's coming, right? Its velocity is pointing straight at me. What direction does the magnetic field point at this position in space? So the r vector is from this negatively charged particle out to that point in space. Okay. Well, let's see. I can see that. Okay, well, let's see what you guys think here. Let's do up, down, left. Let's put up, down, left, right. See what we think, or something in between. Oh, it's not going to work here. So let's not try to make up choices. What direction is it going to point? Well, this is like current, right? The current is coming. This charged particle, the velocity vector is coming out of the page at us. So it's pointing at us. But remember, the vector that we care about is not the velocity of the charge. Remember, it's QV. Right? This is the term that we care about in that right-hand rule. What's the direction of QV? Well, if Q is positive, this vector QV points in the direction of V. If Q is negative, then it flips the sign. So QV is pointing into the page here. So when I use my right-hand rule, that my index finger points not technically in the direction of the velocity, it points in the direction of the velocity times the sign of the charge. So my index finger has to point into the page. Points into the page here. And then if I point my middle finger in the direction of R, I end up with a magnetic field that points something like this. And if I pick different positions, right, I can do that now. Here's R. Again, my index finger is going to point into the page. Okay. R points up like this. I get a magnetic field that points in this direction. And if I fill this in, what you'll find is that I get this circulating pattern for the magnetic field, just like we might expect. Okay. I have the B field circulating around this moving charge, or this kind of current that's flowing out of the page. Because it's a negative charge, though, it circulates in the opposite direction that we would expect from, say, a positive current. So my finger, if I use the finger method, my thumb has to point in the direction of QV, which is into the page. And so my fingers are going to circulate in the direction that we see from that magnetic field there. Okay, we're going to stop there for today. If there are any last questions, you're welcome to stick around and ask them to me. Otherwise, you're free to go, and we will continue with this chapter tomorrow. Thanks, everybody. Have a great day. Bye now.